All right, AP Chem, if you missed office hour this morning, this is your walkthrough for the information you need to be able to answer the questions if you choose to do the textbook assignment this week. And if you do choose the textbook assignment, you're going to be using Einstein's famous equation, energy and its relationship to mass, which he came up with without doing experiments on it. It wasn't proven until a little bit later after he came up with this idea. But the idea is this, that mass is just another form of energy. And you can convert mass to energy and back and forth. And the relationship is this equation here. And the mass needs to be in kilograms if you plug it into this equation. Speed of light is in meters per second. And I would jot down this conversion here at the bottom. One atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. The reason you want that, mass needs to be in kilograms in the equation, but in chemistry, we're dealing with extremely small masses for atoms, and those are atomic mass units. So you're going to have to be able to convert from atomic mass units to kilograms. Now, how does this equation actually work? Well, in nuclear reactions, some of the mass actually disappears. So you start out with a nuclear equation, and on the left side of the equation, it's not going to be the same mass as on the right side after the reaction has occurred. And conservation of mass is not working for a nuclear reaction. It's only working if we consider what amount of mass gets converted to energy. And so to do that, you need a chemical reaction, and it needs to give you this information in the problem. And we're going to look at one for an example here. This is uranium, and this is the fission of uranium. So fission of uranium involves a neutron being absorbed by a uranium atom. And once it gets absorbed, that atom becomes unstable, and it rips apart and makes two smaller atoms, a barium and a krypton atom. And then it shoots off three more neutrons. And what happens, you can see how this can be a chain reaction in a nuclear reactor. If you have uranium in high concentration, this single uranium atom is surrounded by other uranium atoms. And when that neutron hits the uranium atom and splits it, and three more neutrons come off, well, these three neutrons can go find other uranium atoms and split three more uranium atoms. And that would end up producing 9 neutrons. And those 9 neutrons would go on and do that again. And you'd have a chemical reaction or a reactor that continues to react and increase the amount of energy that gets produced. Well, where does that energy come from? It comes from the difference in mass on the left side and on the right side. As the element rips apart, it decreases the total mass that the element has. So let's take a look at that in a little bit more depth. Something you need to be aware of is that a neutron by itself, not bound in the nucleus of an atom, is a different mass than a neutron or a proton that does get bound in the nucleus of an atom. And so the neutron mass, it's given on your homework problem sheet. You just need to look up the mass of that neutron, and here it is on my little table here. You can see it's the same on both sides here. A neutron by itself always will weigh the same mass. But once it gets in the atom, it changes its mass a little bit. Some of that gets converted to energy to bind it together, which we'll talk about in a second here. But the mass of that element, you cannot add up the masses of all the neutrons and protons for uranium to get this mass here. So this has to be given to you in your problem. Don't try to calculate that by hand using the mass of neutron and proton. You'll get a different number. And so this is our total mass of the reactants. Add those up, and the total mass of the products is a little bit less. And if you subtract those two, this is the amount of mass that got converted to energy in this particular chemical reaction. That's where this energy comes from. Well, how much energy is that? Well, we need to use Einstein's equation to take the atomic mass units here and calculate the amount of energy. And so we're going to take atomic mass units and convert them to kilograms first. That's our little ratio that you had on that first slide. And once we have kilograms, we can plug that into Einstein's equation, E equals mc squared. And our mass is going to be our calculated mass in kilograms. The speed of light's always the same. It's constant. You square that, and you hit enter, and you get a really small number here. It's 10 to the negative 11. You might be saying, well, that small number, I thought nuclear reactions produce a lot of energy. Isn't this a little bit of energy? Well, this is for one uranium atom to react. And we know in chemistry, one atom is a significantly small amount of reaction. We usually compare energies in the amount of moles of a particular compound that reacts. So what would happen if a mole of this react? Well, we multiply this by Avogadro's number, 6.022 times 10 to the 23rd, and we get this, 1.66 times 10 to the 13th, which is an extremely large number, joules per mole. Usually we're in kilojoules per mole when we do thermodynamics. So in kilojoules per mole, this would be 10 to the 10th power. Now, if you remember from our thermodynamics unit, most of our chemical reactions, the most exothermic chemical reactions, were producing kilojoules in the hundreds of kilojoules. So we're billions of times more energy for this particular reaction here, a nuclear reaction, than we are for a chemical reaction. And that's why they want to pursue that for nuclear power, and why nuclear power plants do such a great job is because you don't need a lot of uranium to react to produce a lot of energy. You do need a lot of coal in a coal-fired power plant or something else like that, because the energy is less for a chemical reaction. So that's how you do your energy equations. Every problem is going to look very similar to that. The second thing you have to do is calculate mass defect and binding energy in an atom. And what this is when a nucleus in a chemical reaction or in a nuclear reaction, when a nucleus forms, some of the mass of the separate nucleons are your protons and neutrons, is converted into energy. And that's our strong force. We mentioned that last week in that intro video. But the strong force, we know of Coulomb's law, the attraction between positive and negative charged particles. That creates some force of attraction. But the strong force, the force of attraction in the nucleus of an atom, is extremely stronger. So if you take a proton and a neutron and you get them really close to each other, when they bind together, some of that mass, their initial mass, gets converted to energy, and that energy is called binding energy. The amount of mass that gets converted in that is called the mass defect. In other words, if you take the mass of those two individually, a proton and a neutron, by themselves before they're bound, add it up, and then add up the mass after they're bound, you're going to find that the mass is less when they're bound together in a nucleus. And that amount of energy is called the binding energy. Something that you want to jot down here is a new unit of energy related to the joule. It's extremely small. It's called an electron volt of energy. And 1 mega, capital N, is 1 mega electron volt. That's a million electron volts of energy is equal to 1.6 times 10 to the negative 13th joules. So it's an extremely small measurement of energy, and that allows us to look at a singular atom at a time without having this power of 10. We're in whole numbers here. So 1 atomic mass unit of defect, if you use Einstein's equation, you can plug that into Einstein's equation, this in kilograms, and figure out how many joules that is, and then convert to mega electron volts, and you get this. So this would be a useful ratio here for these problems. 1 atomic mass unit, if you lose that much mass in an atom when it binds, you get 931.5 mega electron volts of energy. The greater the binding energy holding the nucleus together, the more stable that particular atom is. And if you look at all of the atoms on the periodic table, or all the elements, you'll get a curve like this for binding energy. And binding energy is the highest for iron. So this is the most stable element on our periodic table. Most stable nuclides are right next to iron. And then all of these elements behind it are too small. So they don't have enough protons and neutrons to create a really high binding energy. And all of these ones can fuse together. Two of these could combine and get to be a larger nucleus and make something that's more stable. So fusion occurs on this side. And then our nuclear reactor, here it is, our uranium on this side. This is going to undergo what's called fission, ripping apart of the atom. So it gets smaller atoms that are more stable. And that's what happens in a nuclear reactor. And so all elements are tending to become more like our iron for stability of the nucleus. So let's look at an example of how we calculate binding energy. In this problem, they want us to calculate the mass defect, how much mass is lost when it binds in the nucleus, and the nuclear binding energy per nucleon. What does that mean? Per particle in the nucleus, so per proton and neutron in mega electron volts for carbon-16. And it gives you the mass of carbon-16. We wouldn't know this off the top of our heads. You'd have to have that given to you in your problem there. So we know the mass. We also know the mass of a proton and neutron. This is given to you in your homework sheet. So just look that up. So what do we want to know? We want to know the mass defect and the binding energy. And the process is pretty simple here. Don't worry about those equations here. I'll just show it to you. This is how you solve it. I'm going to take the total number of protons and the total number of neutrons in this isotope. How do I know that? Well, I look up carbon on my periodic table, and I know all carbon has 6 protons. So that's what my 6 is right here. And I'm going to multiply that by the mass of a proton if it was not bound in the nucleus. So this is the mass of a proton by itself with nothing bound to it. And so if I multiply it out, that will give me the total mass for my protons. The neutrons for this, if the total mass of the compound is 16, or the element, that particular isotope has 10 neutrons in it. And the neutron mass is right here. It's a little bit different than our proton mass, so we multiply that out. And those two combine to give me the total mass of these individual particles if they're not bound together in the nucleus. Well, the problem gives me the mass of the isotope bound together. It's right here, and it's less than that. So I subtract these two, and this is my mass defect. This is how much mass is converted to energy when those two bind together. From that mass defect, I can use my ratio for the mega electron volts for every atomic mass unit that gets converted to energy. And this comes from Einstein's equation. No need to plug it back into the equation, just use this ratio. And this is the amount of binding energy that a carbon-16 isotope contains in the nucleus. So all of this energy is holding that nucleus together. Well, how much is that per nucleon? Well, a nucleon is the number of particles in the nucleus. So the total number of particles would be 10 neutrons and 6 protons, so 16. So I'm going to take my total binding energy and divide it by my 16. Let me move this so you can see here. Divide it by my 16, and this would be the number of mega electron volts for each proton or neutron holding it together in the nucleus, and it's 6.9. The higher this number, the more stable. The lower the number, the less stable that particular atom is. So that's how you do binding energies. You could pause the video if you wanted to and try to do that again here for iron 56, and I'll show it to you here in a second. See if you can calculate the binding energy per nucleon. So for iron 56, what we're given the mass of it. We know the mass of proton and neutron. What do I want to calculate? I want to know how many neutrons and how many protons are in iron 56. So I'm going to look that up on my periodic table and look up how many protons does iron have. And you'll find that iron has 26 protons. Those 26 protons times the mass of a proton by itself, plus the 30. Why 30? Because 26 plus 30 gives me my 56 for my atomic mass, 30 neutrons, and I multiply by their mass. And then I subtract the actual mass of the isotope, and the difference is 0.52844, so larger. More mass was converted to energy for iron. Convert that to mega electron volts, AMUs cancel, and I get 492. Well, how much is that per proton and per neutron? Again, divide that by the total number of protons and neutrons in the isotope, and you get 56 there, and we get 8.79. So this is much higher than our last one for carbon. And that's on that graph that I showed you. That's that peak on the graph. Iron has the greatest binding energy holding those protons and neutrons in the nucleus for any other element on the periodic table. And that's what makes it most stable. It's not going to leave that for them. So what can this be used for? I'll just go through this quickly here. Nuclear fusion. If you grab small elements, you can use nuclear fusion. You can read through, so I'm not going to go through all of this. But small elements, the key concept here, those small elements, when they combine, it produces 10 times the energy. So why would we want to pursue this? It's 10 times the energy as fission. So a nuclear reactor that has uranium in it, the nuclear fusion is going to have even more energy than the uranium reactor. And if you could get a reactor running for this, then you could produce a lot of energy, and you'd be a billionaire. And there's lots of people who are producing this, or trying to produce this in experiments. Now, this happens all the time in the sun. And it takes hydrogen isotopes and to produce helium, and it looks like this on the bottom. The thing that's beneficial about this is the products, the helium and this neutron, are non-radioactive. So that doesn't occur in a fusion or fission reactor with uranium. You're going to have radioactive products at the end, and we have to store those for a long period of time. We don't know what to do with them because they last a really long time. They have really long half-lives. So this has no radioactive byproducts. Not only would you have 10 times the power, but you wouldn't have to deal with those byproducts. This is a great source of energy. Lots of people are pursuing it. The problem is it requires extremely high temperatures for this to occur. We have to get these particles going so fast that when they collide, those individual nuclei will run into each other and fuse. And that requires extremely high temperatures. And we know that that happens in the sun. But how do we get that to happen on Earth? Well, they've done it before, but it's only been successful in the hydrogen bomb or in extremely small samples. And the amount of energy required to get that high temperature is not equal to the amount of energy they get out of the reaction yet. But they have ideas for doing that. They can take this fusion reaction, and one of the problems is you can't make a container that will remain containing this really hot plasma. It'll melt it at that high temperature. So how do I make something that hot that I can contain? They don't contain it in the hydrogen bomb. It just explodes. But we want to contain that if we want to use a reactor. So they've designed reactors that will actually contain plasma using a magnetic field. And it basically keeps the plasma in a little ring here, and it's spinning around in a magnetic field at high speeds. And then that extremely hot temperature doesn't have to be in contact with the container, and they can keep that plasma really hot and produce fusion. Are they doing that? This is a picture of one that has been developed, and They're trying to do experimental tests with it. They're developing the largest one in the world in southern France right now. It looks like this is a construction project. It's about halfway done. It's extremely large. These would be stories here. You can see a crane in the background. This is an extremely large facility, and there's lots of research funds that are going towards this, and countries are donating to it to try to get this technology produced. So another side note, you can artificially produce atoms by bombarding them. So take an alpha particle and get it going really, really fast, run it into nitrogen. And if you get it going fast enough, the nitrogen will actually fuse with it and make a new element. And that's how they produce the really large elements on the bottom of the periodic table, californium. They produce those by ramming them together. And that can happen in a couple of different devices. This would be one of them, a linear accelerator. It takes a source of atoms like alpha particles. And there's my alpha particle. It changes the charges, and it gets it going really, really fast and hits a target at the end. And at the end, that target would absorb it, and it produces massive atoms for a short period of time. This is a picture of it. I think this one's like 2.5 kilometers long. But a better way to do it, and there's a lot of these in Europe. The largest ones are in Europe. It's a cyclotron, and basically takes a target and it goes around in a circle. And if it goes around in a circle, you have a greater distance that it can travel, and you can get it going even faster, and it spins around and hits the source in the middle. I'll skip over this. We don't need to know our decay series here for nuclear reaction. I just want to mention some things about detecting radioactivity. So there's certain devices that get worn by medical professionals to detect whether they're in a radioactive environment. Maybe you've seen this before if someone's an X-ray tech, and they can wear those, and it could be a film badge. A film badge basically changes color when radioactive rays hit it, and they'll be able to tell how much of it has been exposed. But there's other devices as well, and this is one that you want to be aware of. You don't have to do any math with this, but this is how they get the values that you're going to be doing in your homework assignment for how many counts or how many decay events happen per second or per minute or per hour. And they'll have those values for you in your homework. I'll show you one example of that here. But it's called a Geiger counter, and a Geiger counter is a device with argon atoms in it, and argon is a gas that doesn't conduct electricity at all. But if it gets ionized, it'll conduct electricity, and that can happen if you have a particle, a radiation particle, that comes in and hits one of the argon atoms. It'll ionize it, like an alpha particle comes in. And when it gets ionized, this device will detect that argon gas now being able to conduct electricity. In other words, it ejects electrons off of the argon, and it gives a little signal to the device. And the device actually clicks. It sounds like a click. We have one of these at school. I would have showed this to you if we were still at school, but it clicks every time there's radiation around it. Now, there's background radiation always occurring, but if you put this next to a radioactive element, like our little laser pointer here, it's going to start clicking really fast. And so they would use this if there was a nuclear event that caused radiation or radioactive material to get into the environment, and they're going to detect whether they are in the presence of radiation. They could use a Geiger counter. But on a more specific case, they can use a Geiger counter to put a sample in a similar device that will measure the amount of radiation that sample is producing. And they can count how many decay events are happening every minute or every second. And from that, they can predict a half-life for a radioactive isotope. So if they know how many particles are in the sample, and they know that they got one click every minute, they know how many particles are decaying over a given period of time, and they can calculate half-life for the nuclear isotope. And that's what you're doing for some of your problems. So that's how they detect it. There's one other way to detect it, scintillation counter, which is, let me go back here. It's basically a chemical that can store that radiation in it, and it gives a flash of light when that radiation releases. So these ones would be a long-term counter, and you can wear these, and the light gets basically trapped by an ionic structure, or the radiation does, and then it releases it with a flash of light, and it can count that flash of light. Okay. So there is natural radioactive decay. I won't go through this. Even the food you eat, you can look it up, and if you're interested, look up potassium-40 in bananas. But the thing that we care about is how many counts with a Geiger counter, how many counts per minute. That tells us how fast it's decaying over time. And if you think about this, a radioisotope that decays really fast, if I had 1 gram sample of it, or 1 mole sample of it, it's going to have a lot of counts per minute. But a radioactive isotope that has a half-life on the order of millions or billions of years, it's going to have very few counts per minute. And each radionuclide has its own particular length of time that occurs on. That's called the half-life. Everything that decays with a first-order kinetic rate law. So just a refresher for those rate laws. I'll walk you through how to use those equations again to do your math here. And how do we know that this is not a chemical reaction? Chemical reactions for kinetic rate laws, they speed up the hotter we get it. So you get a sample really warm, and it speeds up how fast the chemical reaction occurs because the particles are running into each other more frequently. But if you speed up or heat up a radioactive sample, it doesn't change how many counts you have per minute, which means that that particular radioactive decay event is not a chemical reaction. It's just something that's randomly, spontaneously happening for the inside of that nucleus ripping apart at any given period of time. It doesn't matter how many times it runs into something else or how hot it is. And so radioactivity is not a chemical reaction, not like we were talking about earlier in this year. It's a nuclear reaction. And we don't care about how warm it is. So let's take a look at how we do these calculations using radioactive decay for your kinetic. So the rate law, I drop this down, rate equals K times, usually it's K times the concentration of reactant. But now we're going to be talking about how many nuclides break down over time. So N is the number of radioactive nuclides raised to the first power because we're first order kinetics. And there's only one thing here. There's no multiple reactants. It's only one thing that's involved. So that's my differential rate law. These are all first order. So the half-life matches our first order half-life equation. And the half-life can relate to your K value with this equation. Now the half-lives are known. So oftentimes you can plug in the half-life, figure out what your K value is, plug it into here, and you can figure out your rate, how many decay events are happening per second or per minute or whatever it is. Shorter half-life, the faster it decays, and they call those samples hot samples. This is your integrated rate law, and your integrated rate law would be the natural log of the number of isotopes at a given period of time divided by the number of isotopes that you started with. So this is the fraction of isotopes you have left equals negative K times T. Or negative K times T also equals the natural log of the rate, the decay events per second, divided by the initial rate that you would have had in your original sample. And I'll show you what that looks like with a couple examples here. So just so you know, there's a range of half-lives from really long to really short. This is what it looked like for radioactive decay over time. The decay is exponential. So every half-life that occurs, you get half the amount of material. So if we start with 60,000, when we're at 30,000 here, we're at 2.7 days, and that would be our half-life. Let's take a look at an example here. So you're going to have examples that give you a mass, and they want you to calculate a new mass at a new time. So we have a mass 1.35 milligrams of plutonium, and they want us to calculate the mass that will remain after 5 years. Now you have to know the half-life for this particular radioactive isotope. And in this problem, it's not given to you in the problem, it's right here. They didn't state it up above though, but our half-life is 2.86 years. So you could do this. You could say, well, 2.86 years is one half-life. This is approximately 2 half-lives. It's a little bit less than 2 half-lives. So if you took this number in one half-life, 2.86 years, it gets cut in half, so divide it by 2, then divide by 2 again. That would be if 2 half-lives occurred, and we're something less than that. So we should get an answer really close to that, but less than that. So let's do our math here to calculate that. What should we do? We want to find how much is left over. So we want to take our half-life and get our K value. What is our K constant? So we can use our equations. Once we know our K value, we'll use our initial concentration and our time, and we can calculate our mass that's left over at the end. So to get our K value, we use our 1/2 equation, and to get our time and relate it to what mass is left, we're going to use our integrated rate law. So T, if you plug that in and solve for K, you get K equals 0.693 divided by our half-life, plug in our half-life, and just notice my years here. This is per year. So our K value is per year. That means that we need to use years when we plug it into our integrated rate law. Whatever your units are for K, for time, that's what our T has to be in for time. So we're going to use that value, plug it into our integrated rate law. If you don't have a calculator that has the solve command, you might just write this. For natural log, you take E raised to both sides, and you get E raised to negative KT, and then multiply by your initial concentration, and you get this equation here. This is a decay equation, power decay equation. So I know my initial mass, E raised to negative K, I know what K is now, and I know what T is. I want to know after 5 years has occurred. Plug that into your calculator, hit enter, and you get 0.402 milligrams left over. And that's a reasonable amount. The units are correct, they match, and they cancel each other. And it makes sense if you divide this by 2 twice, it's going to be something less than that. Okay, hope that helps. If you want to do another one, you could try to solve this one and pause the video. And I'll just walk you through it real quick. Again, we know the initial mass. It's the exact same process here. We're going to calculate our K value using our half-life, use the integrated rate law, and our initial conditions. In this case, we're given days and then weeks. So we need to do a conversion here. Your half-life is in days, so that means my K value is going to be in per day. And so I need to convert my 5.4 weeks into days, which would be 37.8 days. And now that I have the same units, I'm going to use the same equation here, a new initial mass, and then my K value with the correct units of days, and you get 0.011 grams. And that's how much would be left over. So units work out, and it's about 10 half-lives that have occurred, and this is the correct sample. When would this ever be used? In nuclear medicine, they use radioactive isotopes all the time. And someone has to know, it's a nuclear physicist, a medical physicist, that actually does the calculations to figure out how hot that sample is, how many radioactive isotopes are left, to figure out what amount or what mass needs to be given to the patient so they actually get the correct number of radioactive atoms in there. And one of the ways they do that is they do it with counting the number of decay events. But then once they know their initial concentration, they can calculate how much time has occurred and very precisely figure out how much is left over of the nuclear isotope. And then they would figure out how much of that sample to give to a patient. Okay. Another way that we use this is radiometric dating. I'll just mention this quickly. Radiometric dating, if we know how long it takes for this process to occur, and just for example, let's say that we knew that we had 10.24 grams of radon to start, and you come back sometime later and you had 0.011 grams, you could use this process just backwards and solve for the amount of time, and you could say, oh, I know that 5.4 weeks has elapsed for this to occur. And that's used for radiometric dating. I'm not going to get into it very much here, but it uses half-lives for that. And different isotopes, some isotopes with long half-lives and some with short half-lives. One of the assumptions they make to do radiometric dating is they have to assume what the initial conditions look like. If I go back to this equation here, if I didn't know that this was 10.24 grams to start, this value here at the end is not going to give me any information because I don't know what my starting amount was. This could be, if this was any value, I'm going to have some other time here that occurs to get that remainder left. So that's an assumption that they make for radiometric dating. They have to be able to assume that that's a certain amount. So radiometric dating for carbon dating, they use carbon-14 with a half-life of 5,700 years. And this is a short half-life, so this, I believe they can go up to tens of thousands of years, about 50,000 years. I'm not sure for this for accuracy, but they know that the carbon-14 always decays at the same rate. And carbon-14, just so you can skip this if you want to, you don't need this for your homework, but carbon-14 is produced in the atmosphere when sunlight hits carbon atoms in the atmosphere, like in CO2. Then a plant would uptake that CO2, the carbon-14 would then be bound to glucose or starches. An animal would come and eat that, and the carbon gets incorporated in the animal's body, and that's where carbon-14 comes from. Once that animal dies, so this is the process, they're still living, they get this carbon-14 to carbon-12. Carbon-12 is your stable one. This carbon-14 to carbon-12 ratio that's constant because it's relatively constant in our atmosphere for a given time. Now, it does change over centuries. So if you go back a couple centuries ago or thousands of years, carbon-14 in the atmosphere will be a different amount. But the CO2 in the air ultimately goes in the organism. If the organism dies, then they're not taking up any more carbon-14 that's produced in the air, and this starts to decay over time. And so that ratio decreases over time. They can measure that ratio and predict how long ago that animal's life. Oh, and here we go, 50,000 years old. Yep, about 9 half-lives is what they say that's accurate to. Okay. So let's look at the last type of problem that you're going to have. An ancient skull, let's use this to calculate how long ago this occurred. An ancient skull gives 4.5 disintegration, so decay events per minute per gram of carbon. If a living organism gives 15.3 decay events per minute per gram of carbon, how old is the skull? Why would the ancient skull have less? Well, it has less carbon-14 in it. After it's sat for a long period of time, the carbon-14 decreases, and I get less decay events over time because it's just less of the radioisotope. So how do I calculate this? Well, the first assumption that's made is that the living organism has the same decay events or same ratio of carbon-14 that the ancient skull would have had when it was alive. And then I can use this ratio of rates here. This is kind of confusing with their math here, so I'm just going to walk you through it here. You can use the integrated rate law here. If you know your initial rate and your final rate at a given time. So initial rate would be on the bottom right here. This would be my 15.3 disintegrations per minute. And then I now have a rate of 4.5. That's going to be the ratio of the sample, it's equivalent to the ratio of how much of the radioactive isotope is left. And so I'm still going to get my K value here, and it gives it to me in years, 5,730. That was on a previous slide there. And I can get my K value for carbon-14, and then I can plug that into my rate equation. Now, this math looks like a mess here, but all they're doing here is plugging in the rate on the top here, rate at the time t, which would be 4.5, and then the initial rate would be 15.3 if we had all the carbon-14 we should have had, and then we just calculate our K value and we can solve for t. And if they do that, you get 1 times 10 to the fourth, which is 10,000 years. And that's how you do your math for that. That's your last type of problem on your homework. I hope that helps. Email me if you have any questions. And good job making it through this year. And enjoy the rest of your week.